Okay, in the previous video, we saw volumes by slabs. Now we'll kind of generalize that to volumes by, volumes for rotation, or solids of rotation. Okay, it's a little bit more formulaic than volumes by slabs because we have more reliable cross-sectional areas. Namely, you can use these rotational solids or solids of revolution. This formula will always work on those because we have a circular cross-sectional area. So let's look at this example. Find the volume of the solid formed by rotating the region described below by the x-axis. The key word is rotating a region around an axis. Okay, so we're rotating about the x-axis. We've got, this is our region, is y equals square root of x between 0 and 1. So this is the curve y equals square root of x. This is 0. This is our value of 1. So the region where, or the solid we're actually interested in is this one. And that being the case, we realize we've got circular cross sections that we can deal with. Now, you always want to sketch that circular cross section to have some idea of what we're dealing with to set your integral up. So we have a point xy on that circular cross section. That cross section's got a thickness dx. We just put that there to help remind us what this thing is doing, right? What it really represents. And xy they're related to each other through y equals x to the 1/2. So we can convert between these two variables if we need to, thanks to that relation. Now, the area of this cross-sectional area in red here, this cross-sectional region, I should say, is the radius, r, right, of that disk, which is actually just equal to y, right? It's the distance from the x-axis. And so then we know that the cross-sectional area of this circular region is a equals pi r squared. Well, if y is equal to r, then it's pi y squared. Now, again, remember this is dx, and this helps keep us honest here. We know that y is equal to x to the 1/2. So when we plug x to the 1/2 in here, we get, well, just x. So we see that happening off to the side. So we needed that in terms of x because we're going to integrate with respect to x here. That's the reminder of what variable we need our area function in. So we get a very simple area function. When we calculate that integral from 0 to 1, we end up with pi over 2. Okay, so let's see a very similar problem. What happens if we rotate the other way? So this is just to point out that if you rotated about the y-axis instead of the x-axis, thinking maybe that would be easier, or there'd be a faster way through the problem, you would be mistaken to do so. You'd have the wrong solid. So also, it's just a good example of rotating about the y-axis and learning how to handle that situation. Okay, so rotating this same curve, y equals root x between 0 and 1 around the y-axis, well, here's that curve again, but instead of going around the x-axis to form the solid we had last time, we're going around the y-axis, and that's forming this sort of concave solid. Okay, so it doesn't necessarily have to have the same amount of volume in it as the other solid. It's a different looking object. So, and this will generally be the case. So in our case now, we want to think about where our circles are. Well, our circles occur as horizontal slabs, horizontal slices of this thing, thanks to the way we've rotated. So the circles always show up perpendicular to the axis of rotation. So that's a nice way to think about it or spot it. Sketching these is almost always useful, right? It's pretty much imperative to be able to sketch these. So definitely try to get at least a reasonable sketch of the graph of the curve at least. Okay, so dy, we mark that out to remind us that we're going to integrate along the y-axis from 0 to 1 to pick up all of our circular slabs here. And we need to talk about the area of one of these cross-sectional guys. And this is this distance from the y-axis out to the blue curve, y equals x to the 1/2. So we put a point xy there generally to mark where we are on that circular region and how we're going to relate that through our function. And we know that the area with respect to y, well, so far we could just say it's pi r squared, even though that's not in terms of y. We know we want to arrive at a function in terms of y. And r squared, again, is just this short little distance here. It turns out that's actually the x value, right, from the y-axis to this point xy. So this is pi x squared, but we know we want this area function in terms of y. So we need to convert it. And in order to convert it, we take both sides to the fourth power, and we have that x squared is equal to y to the fourth. That way we got an x squared. That's why we took it to the fourth power to match that. And we plug in y to the fourth here times pi. And now we've got an area function in terms of y as we desired, which matches our dy. And we can run our integral through and we get the volume as pi over 5. And note that this is in fact a different answer from the previous problem. So rotating on different axes will result in different solids, which result in different volumes. So be very careful if you switch axes, or be careful to understand what you're rotating about in a problem. Okay, so we've got a couple more examples. The next one is to find the volume of the solid obtained by rotating the region given below about the y-axis. So we have y equals x cubed, y equals 8, and x equals 0. X equals 0 is this line, the y-axis. Y equals 8 is this vertical line, so it caps our solid y equals x cubed, or at least our curve, to be this region. So just to point that out in one distinct region, this is x equals 0, y equals 8, and y equals x cubed. That's the region we rotate first about the y-axis. When we do so, it forms this sort of parabolic cup, or whatever we might describe this region as, right? This solid right here. Okay, so we're rotating about the y-axis, so reliably we've got circles that have horizontal circles with thickness dy. So we can begin this with saying, okay, we've got circles, so the area of these cross-sectional regions is pi r squared. Our radius, again, is just the x value of this point xy. Notice that we're always doing this. We're always setting up this example slab. We're marking out a point xy, knowing with our curve labeled here. And we might use r, we might not. It might help point out who's doing what here, that x is the radius. And then we set up what our cross-sectional area is. And we go step by step. X is equal to r here, so pi x squared. But we know that we've got dy, so again, we want this thing to be in terms of y. And we just need to solve that through our given formula, our given function here, right? Y equals x cubed. This is a point on that curve, so it must satisfy that relation. So when we solve for y in this, or solve for x squared in this rather, we get a y to the 2/3 is equal to x squared. So we have a perfect swap for these two. So now we've got a function in terms of y. And again, that's the hard part. We plug it in down here. Integrate from 0 to 8. This is because we're going from down here to up here. And we're off and running with a pretty easy integral. And it looks like we get 96 pi over 5 in this case. Again, the integrals in most of these problems are not very difficult. It's the setup that's difficult. So let's see one more. This is rotating not on one of the standard axes, right? So we're rotating on an axis that's not x equals 0 or y equals 0. So that, which is a possible situation. So in this case, we're going to rotate about the line y equals 2. So we're rotating about a vertical line. They ask us to find the solid obtained by rotating the given region about the line y equals 2. Here's our given region, y equals x squared. It's imperative that we understand what these regions look like. So sketching this and being able to sketch it is crucial. We really want to do that each time. So coordinate axes are drawn. This is our line y equals x. It's an easy thing to graph, the identity function. This is our parabola y equals x squared. If we didn't remember where they intersected, we could set x equal to x squared and solve for x. We get 0 and 1, and -1 as well. But we're only interested in this would extend this way. We're only interested in an enclosed region, right? So when they state this region and give you just these two curves, they mean the region with finite area. Okay, they won't always state that exactly, but that's what's intended. It's implicit in the problem. So here's our little sliver. We're going to rotate this about the line y equals 2. Okay, and this is going to form a solid that I don't really even want to try to draw, right? It's going to be this sort of big circular thing that looks like this more or less. It's got a flat side in here. It's too hard to draw, but if we sketch at least the two-dimensional situation, it'll help us set the problem up. What we note is that when we rotate about this line y equals 2, we're rotating about a horizontal line. So we'll have these little strips um, that would form disks if we didn't have this y equals x boundary above us. So we'll see what happens there. But instead, they're going to form an annulus, right? So this is a washer, really, that rotates about the line. So we'll be able to subtract this volume, from this total volume, in order to get this little bit of volume right here. That's going to be our goal in the annulus method. Um, but what we notice is, we're going to have circular cross-sectional regions perpendicular to y equals 2, so our thickness is dx. So that tells us we're ultimately going to look for an area function in terms of x. Okay, so the area of one of these cross-sectional situations, and let me just sketch what we have here. So a cross-sectional area of this thing would be a disk like this, and it's got a hole punched out in the middle of it. So you're going to take the area of the outer function, which might have a radius r, capital R, and then minus the area of um, the lesser circle, and you'll effectively remove that punched out area in the middle of it. And that's exactly what we're going to do in this case. So let's see that in action here. Okay, we have a few things going on. We need to identify the radii. The longest radius is this. It's the distance between the line y equals 2 and the curve y equals x squared. Okay, that distance is 2 minus x squared. So we're going from here all the way down to here, right? To a point on the curve y equals x squared. So it's 2 minus x squared is this longer radius right here. Okay, so let's write that down. Pi times 2 minus x squared, quantity squared, because that's r squared. That's squaring the radius right there. So our long radius is this. Our short radius is 2 minus x, the distance from the line y equals 2 to the line y equals x. So this is 2 minus x. That's our smaller radius, the lesser one. And we square that radius as well. And so we've got the area of the larger circle, the outer circle, minus the area of the inner circle, set up right here for what we've got going on in this problem. Okay, and once we've established that, we're pretty much all set. This is our area function, right? The volume, the thickness, is taken care of by dx in the integral. And once we plug all this in, square these terms out, we just end up with another polynomial integral. This is from 0 to 1 because we're going from here to here along the x-axis to pick up this whole region. And ultimately what we arrive at is 8 pi over 15. So the book's got at least an example or two of this. This is one of the harder, more complicated situations we'll do for solids of revolution, but I still think that students have more trouble with volumes by slabs. So pay particular attention to both of these processes. And that was in the previous video, this volume by slabs. But this will be as hard as it gets typically for volumes by rotation.